All right, it's 5:45, so we might as well get started. Hi, everybody. I'm Allison, or Ali Rancourt. I'm a cybersecurity software engineer at the MITRE Corporation. And I want to thank you all so much for coming to listen to my talk. I'm pretty passionate about reverse engineering. It's, what I've focused a lot of my career on. So I'm really excited to talk to you about it. So titled for this talk is From Code to Binary and Back Again, a reverse engineering tale by Ali Rancourt, and that is based on the title from The Lord of the Rings, which is one of my favorite movies. From There and Back Again, A Hobbit's Tale by Bilbo Baggins. So, next slide. All right, so a little bit of info about me. I love pasta, dogs, and Lord of the Rings. I hope you all can relate to that, or at least parts of it, hopefully the pasta and dogs part. A lot of my work at the MITRE Corporation is actually at the intersection of reverse engineering and software development. Sort of a software engineer by trade. That's what I learned a lot about at school. And then I came to MITRE and learned a lot about reverse engineering. So I do a lot of tool development and writing code in order to make manual reverse engineering processes more, less time staking and less manual. So that's what a lot of my work is on. I really love working on teams. I love helping people solve problems. I love teaching people about things that I'm passionate about. So I'm really excited to be here at Day of Security. And I've also done some work in cyber deception, which is another really cool area in cyber that you should totally check out. So what is reverse engineering? It's also called back engineering, the process of where a human-made object is deconstructed to reveal its designs, or for the reverse engineer to learn something about that object. So that's super vague and broad and can be applied to a lot of different areas. And I did toss a poll in the chat to see, who's heard of reverse engineering or not. So if you guys want to toss your answer in there, I'd be interested to see. But it's, like I said, a super applicable subject area, and you can think of it as even mechanical applications, taking apart a remote control. You can take apart the pieces to understand what makes up that remote control and how to get back to the finished product. So another really simple example is a recipe. So you eat a dish at a restaurant and you want to know the components of the recipe and how to build that recipe to get to that finished end result. So we can apply that same thought process to software, and I had to relate food to one of my favorite Lord of the Rings quotes, that hobbits love breakfast, second breakfast, levensies, luncheon, afternoon tea, dinner, and supper. So there's that little graphic there. But we can think about reverse engineering software in the same way, essentially as a dish of food. If you, like with reverse engineering a recipe, you need the tools to build software back up to the point of it being readable code. Cooking, you'll have spoons and knives and an oven and all of those kinds of pieces. You need tools to do software reverse engineering too. You can relate like seasonings and ingredients to pieces of your firmware or your binary, being functions, structs, classes, and architecture, all that. And some of the reverse engineering tools that are applicable here, such as IDA, Ghidra, Radare, and Anger. I'll talk about them briefly later on in the talk, but we'll focus primarily on Ghidra. So why should you care about reverse engineering? I personally think there are a lot of reasons to care about reverse engineering, but the biggest one is definitely the amount of software that we have on our phones and computers and like all of these devices around us. They all have software and firmware installed. So I think it's a really empowering, important piece of knowledge to understand how you can take those apart and really learn more about them and understand what they're doing. And these pieces of software coming from a lot of different. Perfect. Thanks, everyone. All right, so malware analysis, we talked about that a bit. Malware is malicious software that gets installed on a device in order to do something malicious, exfiltrate data, or what have you, try to steal some information. Vulnerability discovery and analysis. is when you're going to be reverse engineering some software and potentially to be doing, the capability development or malicious thing yourself, which is, what a nation state would do in order to enact some form of hacking. You're trying to see if a piece of software has a vulnerability that can be exploited. You could also be doing vulnerability analysis, though, to ensure that what you're working on and what your company is producing is safe. Application compatibility, something we don't talk about so much, but understand how two applications are sharing data. You can use reverse engineering to make sure that protocol is correct, and just to make sure that everything is all set for two applications to run together. Supply chain integrity, very important. I'll refer to the SolarWinds hack that a lot of you have probably heard about. Huge supply chain issue. It impacted thousands upon thousands of companies. And it's really important to employ reverse engineering techniques to ensure that your supply chain remains safe. All right, so what is a binary though? What's an executable? In order to understand what, how to reverse engineer software or to reverse engineer a binary, we're going to need to understand what it is. So for the purposes of this talk, we'll be using GCC, so the GNU compiler collection. It's an integrated distribution of compilers for several major programming languages. I bet a bunch of you have used it. So that example GCC compilation line at the bottom is probably going to be very easy for you all to recognize. And we'll also briefly explore the structure of an ELF file. So it's Lord of the Rings, you guys know. I have to make a Legolas joke. No, not this kind of ELF. I'm talking about executable and linkable format. So ELF defines the structure for your code and everything else that needs to be included with it to run on the machine that it was intended to run on. So, everything your computer needs to understand how to run your program is included in your ELF file. So it's the standard binary file format for Unix and Unix-like systems. I'll be giving a demo in a few minutes, and you'll see that I'm using an Ubuntu machine. So ELF files would be the standard form of an executable on your Ubuntu VM. So just wanted to touch on that briefly. The sections, so .text is where you're primarily going to find your code. So whatever code you wrote in, say, C will be available in .text. Row data is going to primarily be strings, ASCII strings. .data will be like global variables and other data used by the program. And then everything else is for like structural definitions. So we're going to briefly touch on the forward engineering components of the life of a binary. It's really important that if you're going to be doing reverse engineering, that you've understood the way, a binary has come to be. So the first step when you're creating binary is, of course, to translate your English or your pseudocode to your coding language of choice. For our purposes, we'll be saying C. A lot of you are probably familiar with C. It's a pretty standard, language to be using in an example like this. You're then going to compile that C to assembly. This is where GCC comes in handy. But at this point, when you're compiling to ASM or assembly, it's really just still a text file. There's nothing executable about it. It's just that you've moved from, this very readable human language of C to the next level down of being really close to readable by a computer, which is assembly. So then you get to the point where you're going to assemble. So the source code becomes an object file. This is the point at which it's really not strings. It's not assembly language anymore. It's going to be, the readable level of a computer. If you use hex dump, it's going to be a bunch of hexadecimal values, and you're not anymore going to be able to check the file type and see that it's a bunch of strings. And then finally, we end with linking. So when we link, we've kind of put all the components together into our executable that we need in order to run it, which is super important. You need library information. The computer needs to understand where in memory to load it. all of these important parts. So I'm going to shift over to a quick demo, and I'm really hoping this doesn't make my sharing finicky. Do you all see this VM? Awesome, I got a couple yeses. So I find it personally really helpful to actually see examples of what someone's talking about. Really helps me ingest and learn the information. So we're just gonna jump through this Jupyter Notebook. And to start, we're going to have our file re0.c. It's just printing hello. This is just running through the normal compilation steps to get an executable. Cool, we wrote our file. Now we're going to compile it. Remember I said we'd use GCC. Now we're going to execute it. Oh, it said hello. All right. So that didn't really show us at all what happened in the background, which is kind of what I was highlighting in that last slide, understanding what's happening in the background. So this first step, your natural language, English. English.txt, our definition of our program is that we need a programmer script to greet the user. Cool beans. All right, we wrote English.txt. So now we all know if we run, if we try to determine what kind of file that is, it's going to be text, right? All we did was write some words to it. So, and now we can read it. Cool. It's very readable because it's text. So now we're going to transition to pseudocode. Well, I'm not going to step through that because it's very similar to the previous steps, but I just wanted to highlight that you're moving from English to your pseudocode. So you can see it's ASCII text now, but we have that it's going to send hello to the user on the screen, and we have our text there. Now here's where it gets interesting. We have actual C now. So we've written our program, and if you check the file type, it's still ASCII text. And that's because we haven't done any of the other steps yet to get it closer to that machine readable and ingestible level that you would get at to be an executable. If we dump, we get the code. Great. So our first step here is using GCC to compile the source code into assembly. And I'm actually going to post a really quick poll to ask, so how many of you have used or seen assembly of any kind? You can fill that poll out at your own leisure. Just curious how many of you have seen assembly, but essentially what this command is going to do is -s, generate the assembly code, -m32, 32-bit assembly code, which really is the definition of the machine architecture is 32-bit versus 64-bit. We don't need to go into it. Assembly code in Intel syntax. This Ubuntu machine runs on architecture is x86. So x86 is the assembly language we'll be using. So let's produce our assembly. We wrote the file, dump the file type. All right, so it's assembler source, but it's still ASCII text. So we're still at a point where if we dump it, we're kind of able to really read a lot of it, right? So we're in assembly, but a lot of these are human digestible words and strings. We have the file name. I already talked to you guys about like row data and text. We see hello again, which is a string that was from the code. Cool stuff. So we can actually kind of read the assembly by dumping the text here. So now we're going to enter into that stage where we're actually going to get the object file, which is really moving us away from the human digestible, human readable stage of a binary. So compiled assembly to the object file is -c. Compiling it, checking the file type. So now we've gotten to the point where it's an ELF 32-bit LSB relocatable. So that's the first time we've gotten to something that's not like ASCII or text, what have you. So if we read the object file, I wonder what's going to happen. Ooh, looks like a lot of gobbledygook. That's because, remember, we're now at the level where the computer is better at reading it than we are. So if we hex dump, this is what the hexadecimal contents of the file look like. For those of you who have seen hexadecimal before, the computer will try to interpret whatever it can as ASCII, but otherwise, it's just printing out a bunch of gobbledygook. So because it's printing out gobbledygook and we can't read hexadecimal, luckily, people who are nice and like to make applications gave us tools to be able to dump the the contents of object files and executables without, trying to dig through it ourselves. So one of those such tools is objdump. And objdump basically puts it back into a form that we can read and parses that hexadecimal to show us the assembly language. So what we're looking at here is x86. So this is the assembly language, the disassembly of the program that we wrote. Unfortunately, it's not very interactive, but that's kind of a foreshadowing to what we're going to see when we use Ghidra. Now we can link the object file to be an executable. Don't mind that warning, I won't either. And now we have an executable elf. So that means that we can actually run it. It's going to print hello for us. And if we objdump, you can see now at this point, there's been a lot more information incorporated into the executable. We're at the point where we can actually run the program on the computer because it has enough information. So I'm going to pop back into the poll. So 18 people have heard of reverse engineering, cool beans, and assembly. So about a little over half of you have seen and heard of assembly before. So that's cool. So you guys will get a little bit of a refresher, and then folks who haven't seen it will learn something new, which is awesome. All right. Now that we know what a binary is, we're going to start understanding what the journey back looks like. I really like the idea of treating this, whole path as a journey, because you really are. It can be long and it can be strenuous, but just like Frodo and Sam, you try your best to get to the point where you have to be. But sadly, getting back is not quite as easy as getting airlifted by an eagle off the slopes of Mount Doom. My real hardcore Lord of the Rings fans, I hope you guys got that. You can throw me a little holler in the chat if you get that reference. But we also are going to assume that we don't have source code. Companies often don't make their proprietary code readily available online, which is totally understandable. They don't need people stealing their intellectual property, which is what adversaries are constantly trying to do. And then adversaries, sure as heck, are not making their source code available, right? Why would they want to let you know what they're doing? So reverse engineering a binary, sometimes you're going into it pretty blindly. All right. Starting to read a binary. A couple really quick things to remember. Do this in a safe environment like a sandbox or something that's not connected to any network and will not harm your host machine. If you're dealing with malware, you don't want that on a personal machine. And then these are just some immediate tools that we have on hand. Kind of showed those in the last demo. Running file to tell the file type. Strings dumps anything that is identifiable as ASCII. And then objdump gives you the contents as assembly, but like I highlighted before, it's not dynamic. You can't interact with it. Therefore, we need a tool like Ghidra. This is kind of a confusing graphic, but I wanted to put reverse engineering into the same context as I just put forward engineering. We won't spend a lot of time on this, but you can see how going from language to pseudocode to source code to assembly in forward engineering, you can essentially trace those steps back directly with applicable defined steps in reverse engineering. So going from a memory dump, a delinker, a disassembler, decompiler, and then from that above, a lot of human effort to get back to the natural language in the pseudocode. So now here's where The people who haven't heard of assembly before, this time's for you. Super speedy intro to assembly, specifically x86. It's the architecture of the Ubuntu VM I'll be using. Also, all Macs use x86. It's a super common assembly language, so it's a really handy dandy skill to learn. An assembly language is just a type of low-level programming language intended to communicate directly with a computer's hardware. C is way too high level for a computer to communicate with, and assembly is just that next step down to get you closer to machine language. So it's also the last step in the forward engineering life of a binary that's still readable to humans. So there are people, unfortunately not me, who are extremely good at reading through assembly and understanding pretty much exactly what it's doing. So good for them. Go you guys. All right, a couple instructions. Move instruction just copies the data item referred to by the second operand. So in that example, move EAX, EBX, which are just registers, so memory. Moving the value of EBX into EAX. It's just doing boop, booping it right over. So the contents get moved, move. LEA is load effective address. It's a super similar direction. What's on the right gets moved into the left, but this time it's moving the address specified by the second operand. So instead of contents, it's address. Super speedy intro to assembly, once again, continued. I beg the question, at this point, is it speedy? Well, probably not, but that's okay. The JZ instruction is a conditional jump, so it follows a test. Flashback to college, so many stack pushes and pulls. I relate to that. JZ instruction, it's going to jump based on a conditional, so there's probably going to be some kind of comparison that happens before that JZ. A flag will be set, and based on the value of that flag, it will determine what happens next, essentially. CMP is what would be setting that flag. It's comparing two operands and is going to say whether they're equal or not equal, what have you. And then call, easy peasy, calls a function. So that one's my favorite, it's the easiest to remember. And then we're going to touch on some registers. It'll be relatively helpful when we do the Ghidra demo. But EAX typically is the return value. So if something like stir compare, so if you're comparing two strings and you need to know whether you're less than, equal to, or greater than 0, that value will be an EAX. RDI and RSI are typically used as parameter registers for calling a function. So if you're going to pass parameters to a function, two registers used are generally RDI and RSI. All right, some common reverse engineering tools. I don't know if I've said this enough, but Ghidra is my favorite. And a demo is coming up. It's open source, free, and developed by the NSA. It's written in Java. As a software engineer, I really love using Ghidra. It has a really extensive Java API. You can kind of do whatever you want with it. It makes my job way easier developing tools for reverse engineering. So I highly encourage you all to download it, throw in some binaries and see what happens and have fun poking around. IDA Pro is probably the one that gets compared most often to Ghidra. We either prefer Ghidra or IDA. So it has some similar capabilities. IDA does have a debugger, so that's 1+ for IDA that a lot of people like to go with. But the full version isn't free, so you don't get all of the architectures that Ghidra offers. You can use like ARM and MIPS and whatnot on Ghidra, but I think IDA Pro, the free version, only has x86. Anger, also open source and free, so highly encourage you to play around with, but it's primarily known for dynamic symbolic analysis, which is a lot of fancy words to mean that it helps you understand how certain inputs to a program or function get you to a specific output. So symbolic analysis allows you to do code coverage analysis and understand code path throughout a binary. And then Radare is also free and open source. It's GUI-less, which makes it kind of tough to use. That doesn't mean you shouldn't try it out. You totally should. There are a lot of people that like to use it. It's not such a popular tool for me, but I highly encourage you to look at it. Now, the moment you've all been waiting for. We're going to try to reverse engineer a binary, and we want to steal the password from it. Of course, I had to use the scene of The Lord of the Rings, where the clan is trying to get into the mines of Moria. Friend, right? But I didn't use the English version of the password, so try to be tricky. So we're going to try to get into the mines of Moria. Okay. But yes, it does say speak friend and enter. I know. Cool. Back to the VM. We don't need this guy anymore. Cool beans. Okay. Oops. I was supposed to clear that out before I showed you all. My bad. So we have an executable that I created called password demo. Let's run it. Speak friend and enter. Okay. Let's put what was suggested in the chat. Friend. Alas, you didn't find the password. The Watcher in the water dragged you into the depths of his lake. So the Watcher in the water is that thing that had like the big tentacles and like tried to grab Frodo and pull him in, for context. Now, here's Ghidra. Already downloaded and installed onto my computer. I created a Day of Security folder to, Ghidra project to get things going. It's pretty easy to do. You can just say, file new project, and you have a project. It's great. So we're going to dump password demo. I'm going to ask you all, for the purposes of this presentation, to ignore the fact that I have the source code, because normally you would not. Just hit OK. This is a bunch of information that Ghidra has determined about the executable. It's a very standard executable. I haven't done anything funky with it, so Ghidra is really happy in knowing, you know, it's x86. I understand that it's all of these things. Cool. So you just let Ghidra do its thing when it's so sure. Now we can open it up. A little dragon pops up, which is a really kind of fun graphic. Auto-analyzed. So Ghidra is going to do some work to make it so that the binary is already pretty easy to work with by the time we get into it. So we can have it auto-analyze. Just do the default options. Kill the default. All right, so it's auto-analyzed. Now, let's take a look. What do we have? Well, first of all, at least we can scroll, which was a heck of a lot better than objdump, if I do say so myself. We can scroll and move around. There's more information. Some of this could look familiar because we're starting to see the sections of the ELF file, so the ELF header. We can look over here. We see data. We see .text, which is where we're going to go in a minute. Whole bunch of sections. So that's kind of why we looked at the format of an ELF file. So jump into text. All right. So for the most part, when Ghidra has a pretty easy to understand binary, it's going to give you the entry point. The entry point does a lot of setup, assembly type stuff, and just tells you where the computer starts when it executes the binary. We don't really need to worry about that so much, besides the fact that we can see our next move is to call a function called main. So that's pretty helpful. Cool, main's right there. Otherwise, if there are a ton of functions in your executable, you can go to Window and actually look at functions. And here, I'm really sorry if that's super small, but you can see all of the functions in the binary listed, some of these being like libc functions, but we could just double click on main and it would bring us right over. All right, so I don't know about you all, but looking at all of this assembly is kind of confusing. So one thing I like to start with when I'm reverse engineering is to look at the, don't spoil it for everyone, Henna. One thing I like to do when I'm looking at an executable is to understand the structure of the function. So Ghidra has this really handy dandy option called the display function graph. So I'll click on that. And hopefully y'all can see that. Doesn't look too bad. So here's the function call graph. So this is just showing the logical blocks of the assembly. So blocks that, a block of code runs until it hits, you know, a split for an if-else statement, or calls to a jump to another location, or calls another function, what have you. So I'm going to move this guy out of the way, and then we can see it kind of looks like we have two main options here. And we can see that both of them lead to this final case, leave and return, which is the end of our function. So let's pop in here. Oh, it looks like this path has a nice string called congrats. Oh, sorry. Congrats, and this one says alas. So we remembered alas from running the binary that, you know, that kind of gave us failure. So we kind of see these two paths, which was helpful to look at. If we go back to the code here, let's try and follow, you know, up to that point where we had that split. So I'll just point this out right now. We have that compare jump pairing that I described when we went through the assembly. So that's really important to note here, and we can kind of work backwards to see how we got to that point. So let's see, we have a print, so looks like it printed speak friend and enter. We remember that happening when we ran the executable. Booping along. All right, fgets. So it looks like there are two parameters to fgets. RDI, RDI and RDX. And fgets is a function that takes a few parameters, being the buffer, the size of the buffer, and one other thing. So it's actually taking three parameters, but we're calling fget. So that's when we get the information from the command line. Cool. Now we can go down to strcomp. Strcomp, we know, compares to strings. So that's cool. We're going to call strcomp, and it looks like RDI, which is one of the parameters to strcomp, is something that someone already posted in the chat. Melon. I can't pronounce it as well as Gandalf can, but he says like melon or something like that in Elvish. It's friend in Elvish. But so we call strcomp. We're comparing two strings. RAX now has, excuse me, it might be RSI. Either way, one of the parameters to strcomp was the string that was read in from the command line, and that's now getting passed to strcomp. Remember, EAX has the return value for a function, and that at this comparison step is getting compared to 0. Now we have this J and Z. We're going to jump to this label if it's not equal. So you can see if it's not equal to 0, we're going to jump to alas, you didn't find the password. But if it is 0, we're going to hit congrats. Now, to show you all a dirty little secret that makes you know, reverse engineering a tiny binary like this way easier, Ghidra has this cool thing called a decompiler. Now, I don't know how well you can see this. I really apologize for how tiny it is, but that looks really close to C, does it not? You can see there's the printf, fgets, strcomp, the comparison. You can clearly see what's happening here. So the decompiler is a reverse engineer's best friend. You know, it's more helpful in a situation like this where we have a small binary and we're reverse engineering one function. But, you know, if you put it into the context of having a huge firmware file, say you extracted it from like an IoT device or something, looking at the decompilation of a bunch of tiny random functions is really tough. So that's when you're going to employ a lot of the, you know, scripting skills. Maybe you know a certain function has these certain qualities. You can develop a Ghidra script to identify that function and name it, or you know that you want something that's utilizing this specific piece of data. You can write a script, or you know, manually identify which function is using that piece of data. So for example, the congrats string is saved in this executable. Maybe you looked through the defined strings in Ghidra and you saw that. So you saw congrats. Oh, that's a really special string, it seems like. Let's look at that. Well, Ghidra will tell you exactly where it's used in the binary, and you can go there and work from that function. Unfortunately, in such a short talk, it's really hard to show you, all the cool things that Ghidra can do. It's borderline limitless in reverse engineering. So there are a lot of tools and resources online that you all can use to learn more about it. So that ends my demo of Ghidra, but not before I prove that melon is actually the right password. Yay, we entered the mines of Moria, and now we get to deal with the Balrog and all the other evil things that awaits us in there, but still cool, we got through. So thanks for bearing with me through that demo of Ghidra. Someone loves the loader references. Thank you so much. I'm so happy people are appreciating the Lord of the Rings stuff. All right, so now we're just kind of getting to some of the things that are the icing on the cake. What I really wanted to get through for you guys was the Ghidra demo, so I can really kind of break down the barrier of using a tool like that. Sometimes the scariest thing is just opening up and not knowing what to expect, but I hope you all feel now that you can open up Ghidra, you know what to expect, and you can start doing things on your own. So I made that binary myself, and I made it really easy to reverse engineer. And so what are some things that adversaries or other people do to make a binary harder to reverse engineer? A couple things that are used are obfuscation and packing. So obfuscation is the method of using like algorithms or encryption or, and there's some overlap between obfuscation and packing, but encryption or other means of making it so a tool like Ghidra can't just readily identify, can't readily disassemble or decompile or do any of the cool things it can do because there's a level of, obscurity over it. There's something that someone did to make it so Ghidra can't interpret it or other tools can't interpret it. Packing is a method where you actually will use compression to pack some pieces of the binary together. And so what you will have to do is actually potentially reverse engineer the packing algorithm to run that on those compressed sections to be able to load those into memory or load those into Ghidra. So that's actually kind of a fun thing I had to do once. I had to reverse engineer the packing protocol on a binary, and it was a lot of fun because when I got to the point where I actually decompressed all of these sections of the binary, I was able to load it up in Ghidra, and it was extremely satisfying. So that sounds super dorky that I'm saying how fun that is, but reverse engineering is like a big puzzle. If you enjoy puzzles, you'll probably enjoy going through some of this methodology. You can also strip symbols. So symbols are details in a binary that label things and name things. They really allow you to identify, like function names would be included in a binary if you haven't stripped the symbols. So most production level software has the symbols stripped. Not only does it make the executable smaller, it also makes it harder to reverse engineer. Removing debug information. So there's information that needs to be included in a binary in order to load it into a debugger like GDB. So there's an option in GCC that actually allows you to remove the debug information so that you can't use a dynamic analysis tool like the debugger in IDA or or GDB, like I just mentioned. So those are all really helpful things to know about because it's important to realize that not everything is going to be easy to reverse engineer. One last note, doing a string search like we did to find the password, we clearly identified, where that string was. Sometimes they'll obfuscate, just strings when they write the code or something like that. So even strings could be hard to read. So these are just kind of some like info-related backup slides that I wanted to include at the end of my talk to give you all a little more context in the world of reverse engineering. So I included the FireEye and SolarWinds hack as a blue team defense example. Remember I talked about supply chain integrity and how reverse engineering your supply chain is important in order to understand, how people could exploit it. Well, the folks at FireEye had to reverse engineer the supply chain anyway from the SolarWinds software in order to identify where the malicious actors placed the exploit. So essentially what happened was a nation state took a hold of one of SolarWinds update packages, shoved some really malicious backdoor code into a DLL, and bada bing, bada boom, they got their foot in the door, were able to set up command and control, exfiltrate data, and do a lot of really malicious things. So I encourage you to look up this FireEye SolarWinds hack. Google it on your own and learn more about it. It's a really interesting example of a cyber attack, and it's very relevant. Another example is for a red teamer or someone doing naughty malicious things is to exploit a buffer overflow. Extremely simple concept. It's when the volume of data exceeds the storage. So if you're thinking in terms of C or C++, you've established an array of, say, length 10. There's no inherent protection on keeping the size of the data stored in that array to length of 10. So you can actually flow past that and potentially corrupt other variables saved on the stack to be later used in that program. So that's a buffer overflow. Most commonly occur in C++ and C, like I said, because they don't have built-in protection. But adversaries are constantly finding buffer overflows left and right, and they're always getting exploited. So I encourage you all to look up CVEs, so common vulnerabilities and exploits that have to do with buffer overflows, because you're going to get a lot of really interesting information. Okay, so I only have 1 minute left, and I really apologize for not leaving enough time to answer some questions, but I will put my LinkedIn link in the chat. And you all can reach out to me there. I really encourage you to say hi. I'll say hi back, and I'd love to talk about reverse engineering with you all. Thanks so much.